Hey Ramblers! This video covers chapter 3.10 in our textbook and deals with theorems about differentiable functions. You'll remember that differentiable just means it's a function that you can differentiate or take the derivative of. So we're going to talk about four different theorems in this video. One will be an important one called the mean value theorem. The second one will be the increasing function theorem. The third will be the constant function theorem. And the fourth is something we call the racetrack principle. Now, all of these theorems help us get ready for our work in Chapter 4 because this is the last section of Chapter 3, and we're going to get ready to apply the derivative in the next chapter so that we can start looking at functions and determining things like where the maximums occur, where the minimums occur, and get an idea how functions are behaving from the derivative itself. So, Ramblers, please take good notes, pause often, and thanks for watching. One of the most important theorems in calculus is the mean value theorem. And it's kind of hard to understand, or at least hard to understand the applicability of it. But it's important, it's pervasive, and you're certainly going to come across it during the rest of this year and probably next year in college. So let's talk about what it means. The best way to understand the mean value theorem is to think about the definition of mean. Okay, maybe not that. When you think of mean, think of average. So that the mean value theorem takes on some idea of average. And here's the average we're going to talk about. That if we have an interval from A to B, and you were to connect a line from A to B, what would be the slope of that line? Well, it would be the same slope formula that we've had since freshman year. F of B minus F of A, so the change in Y, divided by the change in X. And what the mean value theorem says is there is some point, C, it's between A and B somewhere, but somewhere between them, this point C has a derivative that is equal to that average rate of change. And that's all it says. Let's go through it again. On an interval from A to B, there is, if we looked at the average rate of change, there is some point C where the derivative is equal to that average rate of change. So you'll notice that the secant line connecting A to B has a slope that is the same as the tangent line. So these two lines would be parallel, just like we learned in geometry. They'd have the same slope. Okay, let's take a look at this in more formal language. And maybe this is what you need to get in your notes. But it tells me that if f, that function, is continuous on the closed interval A to B, and it's differentiable on the open interval from A to B. So in other words, this can't be a function that has any points where it's not differentiable, like corners or cusps, and it's got to be continuous, so no holes or no jumps, just kind of our plain Jane average function. Then there must be that number C between A and B, such that the derivative at C equals the average rate of change from A to B. So let's get that in your notes. You might wonder how does that ever get used? And there's actually, it came up once in real life. My family was taking a trip out east, and driving home, we drove through the Pennsylvania Turnpike and ran into a little trouble with the police. The trouble you'd expect would look something like this, but it was actually far less intimidating, and was just a toll booth. These toll booths are located throughout the turnpike in Pennsylvania, and when you get on the turnpike at, your distance is 0, and you get one when you get off the turnpike 280 miles later on the western end of Pennsylvania. So if you take your distance at the end and subtract your distance at the beginning and divide by the amount of time that you spent on the on the Pennsylvania Turnpike, which in our case was we got off at time 3.5 or 3.5 hours, you're going to find that we ended up making a pretty good time. That our average rate of change was 80 miles per hour. Well, this right here is the mean value theorem. And while the toll booth operator didn't quote calculus to us, it had passed as a law in Pennsylvania that by the mean value theorem, there must have been some point between when we got on at time 0 and when we got off 280 miles later, where there must have been some point where our instantaneous rate of change was 80 miles an hour. So they served us with a ticket. And that was a direct application. It's a true story. Okay, let's move on. The increasing function theorem is pretty straightforward. Once again, if f is continuous on a closed interval and differentiable on an open interval. So once again, we're not going to worry about functions that have corners or cusps or holes or jumps. But if the derivative is positive from a to b, then f is increasing. So positive derivative means that the function's increasing. We've known that all semester. Let's not worry about the second statement here, but I would like you to put in your notes that if f prime of x is negative on the interval from a to b, then f of x is decreasing. So it's kind of the opposite of the increasing function theorem, but equally important. Okay, let's move on to the next theorem, the constant function theorem. Okay, this is a pretty simple and straightforward theorem, but it's very important. Once again, suppose that f of x is continuous on the closed interval and differentiable on the open interval, no jumps, holes, corners, cusps, the whole bit. If the derivative equals 0, then f of x is a constant function. All right? Where this is going to become really important is this is going to help us to identify maxes and mins in the next chapter. So this is an important, kind of very self-evident theorem, but you want to make sure it's in your notes and that you kind of understand why that it's true. Okay, let's finish off with this thing called the racetrack principle. Okay, this last principle is as simple to understand as the others, but let's just kind of weed through the wording here. Why don't you pause the video for a minute and just read through this little bit. Here we know that we have two functions, g and h, which are both continuous on the closed interval and differentiable on the open interval. Same as what we've been talking about. But here, the derivative of g is less than the derivative of h. So it says that if g of a and h of a are equal, so that means there's some point a where g of a and h of a are the same y value. So g of a, h of a, it's the same one. Since the derivative of h is greater, it's going to increase faster. The derivative of g is going to increase more slowly. So that means that g of x will be below h of x the entire time until we hit the end of the interval at b. So all of these derivatives really boil down to this. If the derivative f prime of x is greater than 0, f of x is increasing. If f prime of x is less than 0, f of x is decreasing. If f of x is equal to 0, if f prime of x is equal to 0, then f of x is constant. All right? Okay, and if you have two functions, g of x and h of x, if one derivative is greater than the other, then that function is increasing faster than the other. All right, let's not let this get too confusing. Let's wrap up. I hope you took good notes. If not, please rewind the video and make sure you're comfortable with these, especially the mean value theorem and the increasing function theorem. All right, Ramblers, thanks for watching.